Okay, so in this talk, I'm going to discuss some methods for devising scalable models and computational tools for handling complex data streams. And this is work that's coming out of my group in the last few years, done with the students and postdocs shown here, as well as collaborators at other universities and companies. Is this working? Okay, so I think the first thing that's important to hammer home is the fact that time series appear everywhere. This picture here might represent anything from recordings of neural activity over time collected from a set of sensors to observations of human body position as a person's moving around in some scene. And when we're thinking about doing dynamical modeling, there are a number of challenges we're faced with. So classically, time series modeling is really focused just on a univariate or low-dimensional multivariate process. But in lots of modern applications, we're faced with really high-dimensional data streams or large collections of time series. And a question might be, how do we capture the relationships between these different series and how this evolves over time? There are lots of other important challenges like handling irregular grids of observations, missing values, heterogeneous data sources, and there's quite a long list here. These are all what I call big model challenges. But on the other hand, there's the more classical notion of a big data challenge where you have lots and lots of observations. So in the case of time series, really long time series. And the question is, how do we scale our computations to really handle all the data that we have present? And there's also a challenge of how do we handle data as it continually streams in. For the sake of this talk, I'm really going to be focusing in on this idea of scalable relational structures. But we'll quickly touch upon some computational challenges at the end of the talk. Okay, so in the case of IID data, there are a couple canonical tools that have proven quite useful in coping with high-dimensional data sources. And these are really well studied at this point. So one example is if we imagine we have just a high-dimensional Gaussian random vector, then the covariance matrix, this big covariance matrix, is capturing the dependencies between the different dimensions that we're interested in. But instead of modeling a full covariance matrix, one common approach is to assume a low-rank decomposition, which corresponds to low-dimensional embedding of our observations. Another possible approach, was a really simple approach, is to assume that there are some underlying clusters of the random variables where we have correlations within a cluster and independence between the clusters. So this is statements of marginal independence, and these are given by zeros in the covariance matrix. But these statements of marginal independence are quite strong. So instead, often people look at a more general framework, which we've heard about a few times already in this conference, of graphical models, which encode statements of conditional independence. In particular, these statements in the case of Gaussian graphical models are encoded by zeros in the inverse covariance matrix. So these tools have proven really useful for IID data, and we've seen examples of them being applied in the time series context, but I'm going to go through and describe other ways in which these types of techniques can be used to devise scalable dynamical models. So to start with, let's look at this idea of low-rank approximations or low-dimensional embeddings of our observations. And throughout the talk, I'm going to use this little cartoon to depict our time series, where the series of y's represent our observed process, and there might be some latent process that we use to describe the dynamics. So in this part of the talk, we're assuming that we have, sorry, unfortunately it's not projecting all that well. Can you guys see the gray? Not so well. Okay, these are big, long gray ovals. So we're focusing on really high-dimensional observations. So to motivate this, let's look at some MEG data, where a person sits in this chair. There's this helmet with 102 spatially distributed sensors that provide recordings of neuronal activity as a person's shown some stimulus. So in our experiments, we're looking at this to understand how the brain encodes different concepts, like animals, food, and things like this. And so in this experiment, a person's shown a word like cow, and then we get this high-dimensional time series response to the stimulus. Then they're shown another word like apple, get another response to this. And a question is, how does this time series evolve as a function of the stimulus shown? So clearly, we're in a high-dimensional time series setting. But another really important aspect of this application is the fact that there are time-varying correlations between the different dimensions, between the different sensors that we have that we're observing over time. And this relates to ideas of functional connectivity that were discussed earlier. Okay, so let's start by just thinking about scaling up to high dimensions. And the first observation we make here is the fact that these sensors are in essence providing redundant observations. So here I'm just showing a picture of 4 different sensor recordings over time. And we can clearly see the very strong correlations here. And what this motivates is thinking about embedding these high dimensional observations in a lower dimensional subspace. And so this relates to an idea called dynamic latent factor modeling. But before we get to thinking about a dynamical process, let's just talk about latent factor models in the case of IID data sources. So here we're going to assume that we have some high dimensional, we'll call it a p-dimensional Gaussian vector with covariance matrix sigma. Well, a latent factor model assumes that this covariance matrix has the following decomposition into a low rank term plus a diagonal component, where the rank k here is assumed to be much, much less than our observed dimension p. And so in pictures, what we're saying is we're taking this big covariance matrix and we're assuming that we have the following decomposition, which represents a dramatic reduction in the parameterization of this model. And the really key term here is this matrix lambda, which is the factor loadings matrix. So one way to think about a latent factor model is to say that there's some k-dimensional latent factor, just standard normal latent factor, that gets projected up to our full observed p-dimensional observation via this factor loadings matrix. But like I said, that was for IID data. And if we're interested in time series, one common approach is to place dynamics on the latent factors themselves. And then, so there's some evolution to the latent factors, and these are projected up to our observations using the factor loadings matrix, just like before. But one thing I mentioned was for this application, one of the really important things we're trying to capture is the fact that there are time-varying changes to the correlations between the observed vectors. And if we assume just the standard latent factor model, you end up inducing just a static covariance between your observed dimensions. So instead of just a matrix sigma static over time, we want a time-varying covariance. And so to induce this, we're going to just model a time evolution to the factor loadings matrix. So instead of some p by k factor loadings matrix, we now have a p by k array of processes defined over time. So then to get our time-varying covariance, we multiply this array by its transpose and add a diagonal component. But this still represents quite a large set of processes over time that we have to model. Remember, p we're assuming is really high dimensional, a really large number. So p by k array of processes is quite a large piece to handle. So we're going to make another, in essence, factor assumption, which is that this array can be described as a weighted collection of a much smaller set of dictionary functions over time. Okay, so this is the model that we're going to use in our analysis. So this is, on the bottom here, we see the resulting covariance decomposition. Okay, so using this type of model, we can end up inferring things like the following. We're just going to take this sensor as a reference sensor and look at the correlations between this sensor and every other sensor as a function of time in response to the word kick. And what you see is that as the person is processing this word, different parts of the brain are co-activating, and that co-activation pattern changes over time. For people who are actually doing connectivity analysis, I do want to highlight this. This is in the sensor space that we're working. Later we'll get to source space. So if that means anything to you, know that. Okay. But let's get to some actual data analysis here. So for this application, we had 4 different word categories: animals, food, tools, and buildings. And for each word category, there were 5 words in that category that the person was shown. And for each word, the person was shown that word 20 times. We're going to use 15 of those trials to train a word-specific model. And then we're going to hold out 5 trials to test our classification performance, where we're just interested in classifying the word into the correct word category. So chance is going to be 25%. And one thing I want to highlight is don't expect huge numbers here. This is non-invasive recordings of brain activity, really, really low signal-to-noise ratio. So people actually thought we couldn't get any statistically significant performance in this application. This says exactly what I just said, so moving on. So there's 2 different subjects that we had that underwent this study. And here we're showing this word classification performance, where the blue bar represents the performance of a model that allows for a time-varying mean, but a static covariance. The green bar allows for the same time-varying mean, but now a time-varying covariance, but inferred just using standard kernel-based methods. So nothing having to do with our model. But what we see is that there's definitely importance in capturing this heteroscedasticity. But the only statistically significant performance in both of these cases is using our method that not only allows for a time-varying mean and covariance, but does this modeling by embedding things in a low-dimensional subspace and leveraging that. And it even outperforms this powerful SVM discriminative classifier. Okay, so I just wanted to present a few qualitative plots to get to some of the intuition behind what I think is going on here. So here we're showing the same correlation maps that I showed before. We're looking at the correlation between a reference sensor and every other sensor at a snapshot in time. So this snapshot is really early on in the process, and we're comparing the stimulus hammer to the stimulus house. And when we look early on in this process, we see basically no difference. But if we look later in the process, which corresponds to when it's known in the community that people should have been distinguishing between these different words, we actually see different structures. So for the word hammer, we see this bilateral activation pattern that we don't see for the word house. And of course, this differential structure could help with our classification performance. But what I want to emphasize here is, if I think about embedding these observations in a low-dimensional subspace, the way I would do it here is different than how I would do it here. Here, these are the strongly correlated observations, and here, these are the ones that are. So by allowing for a time-varying factor loadings matrix, that allows us to have this change in how we're thinking about embedding into that low-dimensional subspace. Okay, so that was our quick tour into low-rank models or latent factor models. And now I want to turn to a really simple idea of clusters of time series. So instead of that picture of one really high-dimensional time series, in this context, we're going to think of having a collection of time series. It's a subtle distinction, but it's important in how we think about doing the modeling. And we're going to assume that we just want to discover some clusters of these time series. I'll describe what I mean by that in this section. And so this was motivated by a collaboration we have with Zillow, which is a housing company based out of Seattle. And their goal is to estimate house values at really local geographic regions. But a challenge in doing this, in particular, we were asked to estimate values at the census tract level, is the fact that the data are spatiotemporally really, really sparse. So to get a sense of this, we can look at the following table, where we see that over 40% of the census tracts in this is the Seattle metropolitan region that we're looking at, have fewer than 3 observations per month. House sales are recorded in the US on a monthly basis, so that's the time scale we're looking at. And more than 10% have no observations. So just to illustrate this, here's one census tract that had lots of observations. So even though it's a little hard to see with this projector, each one of these dots is a different house sale. And our goal is to estimate the value in this census tract, this red line, over this 17-year period, as well as this shaded red region, which represents our uncertainty about that estimate. So it doesn't seem so hard for this census tract, but if we look at another census tract, here, and it's nearly impossible for you to see this, but just believe me that there are only 4 house sales over a 17-year period. So that seems like a much more challenging problem, clearly. So the question is, how are we going to be able to produce reasonable estimates in census tracts where we have very few observations? Well, the simple approach that I was describing, which is pretty intuitive in this application, is we're just going to discover clusters of census tracts where the dynamics of house values in these regions are correlated. Especially in Seattle, you can think about if you have waterfront housing in one area and waterfront housing somewhere else, they tend to actually behave quite similarly, even if they're geographically not adjacent to one another. So this type of structure, you have very heterogeneous dependencies between regions across metropolitan regions. So what we're going to do here, so I guess I just want to emphasize we're ignoring the spatial structure in this because of the strong heterogeneity that we see across spatial regions. We're just treating it as a collection of time series and trying to discover the relationships between them as a collection of time series. Okay. So let's dig into the model where for each census tract I, we're going to assume that there's some underlying linear Gaussian state space model describing the evolution of the price dynamics. So X is going to be our latent price in census tract I. This is just a standard autoregressive evolution. And then the nth house sale in census tract I at time t, really the log price, is just going to be a noisy version of the value in that census tract corrected by house level covariates. And I want to emphasize that I've hidden some things from this equation. So we're modeling a global trend and seasonality and a lot of other things that are important to this application, but what we're focusing on here is just the residual structure from that global trend. Okay, so going back to our cartoon, we can think of this model per census tract as this state space model where at every time point we have a variable number of observations and often we have 0 observations. Okay, but we don't just have one census tract, we have a large collection of different census tracts. And so instead of modeling each independently, because that wouldn't work well for the census tracts that have very few observations, we're taking these innovations that are driving these latent price dynamics and we're going to jointly model them, stack them up into a big vector. And a question, though, is what do we do with this covariance? Because both statistically and computationally, we can't handle a full covariance matrix. So here is where we're going to start using this idea of clustering. So in particular, instead of this full covariance matrix, we're going to assume that there's a block diagonal structure where if a census tract falls within one of these blocks, it's correlated with other tracts in that block. And if it's outside, if 2 census tracts are in different clusters, then they're independent. So if we take this structure for the innovations, throw it through our dynamical model, what we end up with clusters of time series with correlated dynamics. So in contrast to some previous approaches for doing these types of things, instead of having identical trajectories within a cluster or just noisy variants of that, we're just inducing a structure where there's correlation within independence between. Okay, but one of the challenges here is the fact that we don't know the clustering. So we don't know what are the ordering of census tracts that lead to this block structure, how many blocks are there, what are the size of the blocks. And so to handle this, what we're going to do is we're again going to appeal to a latent factor model, and then we're going to place a Bayesian non-parametric prior to handle the fact that we don't know how many clusters there are. So we're going to take this innovation, so this is the innovation at time t for census tract I. We're going to assume that there's a tract-specific factor loading and then a cluster-specific latent factor process. And then if we think about marginalizing these latent factor processes, this is what induces this block diagonal covariance structure. Okay, so now the question reduces to how do we think about inferring these cluster memberships and how many clusters there are. And for this, we're going to use a Bayesian non-parametric approach using just a standard Dirichlet process, though you could plug in your favorite process here. And I'll just provide very quick background, well, just intuition about the Dirichlet process. So the Dirichlet process allows us to infer the number of clusters from the data while still allowing for new components to be added to our model as more data are observed. In this example, I'm just showing a mixture of Gaussian, so the thing that defines each cluster is the mean and covariance. But in our application, remember the thing that defines each cluster is this latent factor process defined over all time. So that's what we're placing this Dirichlet process prior over. Okay, so that's the model. Now let's turn to our analysis of this Seattle metropolitan housing data set, where there are 140 census tracts, and we have over 125,000 transactions during this 17-year period. I'm going to skip over some of the computational details and just emphasize the results here, where here this is the region we're looking at divided into the different census tracts, and the colorings indicate the different clusterings, where the specific color that's used is based on how much the latent trend in that cluster, the average latent trend across census tracts assigned to that cluster, deviates from the global trend. And each one of these cluster-specific latent trends on a log scale subtracted from the global trend is shown here. So for example, here in this region, we see this red color. This is the downtown region in Seattle. And it makes a lot of sense that during this time period, this was the region that had the most volatility relative to the global trend. And there are lots of other intuitive structures that come out of this analysis. But our interest, like I said, was really in inferring a housing index. And so we can look at using our housing index to predict house sales prices. And what this is showing here is we took the industry standard housing index, which is the Case-Shiller index. And that index is computed at the city level, and you can't even compute it at the census tract level because of the data scarcity issue. But when we look at the computable index and we compare to our predictions, we're showing percent improvement over Case-Shiller, and we're looking at the 5% of census tracts with the most observations, middle 50%, and then the 5% of census tracts that have the fewest observations in the data set. In all cases, we have gains over Case-Shiller, but not surprisingly, most significantly for the census tracts that have few observations, because that's where this clustering, in essence, this multiple shrinkage is really useful. Okay, so we talked about how this really, really simple notion of clustering of time series can have significant impact in applications. And this is actually an idea that I think is pretty underutilized in the literature. But it does make this pretty strong assumption that if you fall into a different cluster, then you're completely independent. So these statements of marginal independence are very strong, and instead, there's often interest in thinking about using graphical models, which instead encode statements of conditional independence. Okay, so now let's talk a little bit about this idea of graphical models, but for time series. And we're going to talk about them in a different way than they've been discussed in this conference so far. Specifically, we're going to discuss a graphical model where every node represents a process that we're observing, a stochastic process we're observing, and we're interested in inferring conditional independencies between these different processes. So one can think about using this, for example, if we have a collection of global stock indices and we're interested in understanding maybe our observations from each of these are the daily returns over time. And if we infer a graphical model from this data, what we're aiming to do in this part of the talk is to say that this is encoding statements of conditional independence between these entire processes from these different countries. Okay, but before we talk about graphs for time series, let's just quickly review graphical models for IID data. So a graph, the nodes in a graph are just a collection of random variables, and the lack of an edge encodes statements of conditional independence. So for example, here we see that there's no edge between random variables 1 and 2. That means these random variables are conditionally independent given x3, x4, and x5. And if we further assume that our random variables are jointly Gaussian distributed, then these statements of conditional independence are encoded in the precision matrix, this inverse covariance matrix. So specifically by the zeros. So here, for example, this gray square is indicating that there's a 0 in the 1, 2 entry, meaning that there's no edge between random variables 1 and 2. Okay, but like I said, instead of graphical models for IID random variables, we're interested in graphical models for time series, where what this graph is encoding are statements of conditional independence between entire processes. And this is going to account for interactions between these processes at any possible lag. And for the sake of this talk, we're going to look at Gaussian stationary processes. So this is just the time series analog of the Gaussian graphical model case I was describing on the last slide. Okay, so the question is, how do we do structure learning? Where by that I mean learn the structure of the graph from data. Well, one could say, okay, I'm just going to take my p different time series observed at some capital T different time steps and stack it up into a big vector and do my standard Gaussian graphical model approach with some structure to get these into different blocks. But there are methods for doing that. So it sounds fairly reasonable, but let's just think about this a little bit. If we look at the covariance of this vector, that's this matrix here, which is defined in terms of these lag covariance matrices. And then what we'd be doing is structure learning based off of this matrix here. But the issue is the fact that this matrix is a TP by TP matrix, where T is the number of time steps we have. So, a very short time series would be 1,000 time points. And P is the number of time series. And again, maybe a fairly small number would be looking at 50 different time series. So that's a 50,000 by 50,000 dimensional matrix. So this doesn't represent an appropriate technique for doing this type of analysis in any scalable way. So instead, what we're going to show is that it's really helpful to take the data and transform it from the time domain into the frequency domain, using, for example, a standard FFT. And then instead of talking about lag covariance matrices, we're going to talk about their frequency domain analog, which are called spectral density matrices. And these lag covariance matrices are defined over time for different lags in time, whereas our spectral density matrices are defined across frequencies, minus pi to pi. Okay, but a question is, what are the conditions on these spectral density matrices that encode these conditional independence that we're interested in? We knew what it was in the time domain, but we don't know in the frequency domain. Well, let's just remember that for Gaussian IID random variables, we said that these conditional independencies are encoded by zeros in the precision matrix. Well, there's this important result by Dahlhaus in 2000 that says for Gaussian stationary processes, if we look at the inverse spectral density matrix across frequencies, and we look at the zeros that are consistent across these frequencies, then that encodes this graph of time series we're interested in. So I'm just stating this a little bit more formally here. Okay, so this result by Dahlhaus gives us the conditions for identifying conditional independencies from these spectral density matrices. But the question is, how do we actually infer this structure from data? Well, we're going to take a likelihood-based approach where first we need to relate our time series to these spectral density matrices, and then we're going to take a furthermore Bayesian approach and place priors over the parameters of our model and do Bayesian structure learning. Okay, so to get into this likelihood-based approach, let's dig into the spectral representation a little bit more. So we're going to take our p different time series that we're observing, transform them into the frequency domain, where here we have our set of Fourier coefficients for each of these different series. And we're going to look at the vector of Fourier coefficients across the different frequencies that we're looking at and stack these up into vectors. And then to define our likelihood, in the time domain, remember we wrote down what the likelihood of our observed time series was given these lag covariance matrices that involve that big TP by TP matrix. Well, when we go to the frequency domain, we're going to appeal to something called the Whittle likelihood approximation. that says that our Fourier coefficients are approximately complex normally distributed vectors. And what this allows us to do, I don't know if I use the word independent, that's the key thing. So approximately independent complex normally distributed random vectors is we're taking this huge full Gaussian in the time domain, and we're able in the frequency domain to decouple across time independently. So we have capital T different matrices, each of size p by p. Okay, so that's our likelihood. And now the question is, how are we doing our Bayesian structure learning? So I first wanted to review what's done in the standard IID case, where typically people place priors over graph structures, and then a prior over covariance matrices. I'll call these graph-constrained covariance matrices because they're covariance matrices where when you take their inverse, they have zeros in the right locations as specified by the graph. And then the generative model says that the observations are just IID normal with covariance sigma. Well, in our case, we're going to place exactly the same prior over graph structures. But now what we need is we need a prior over these graph-constrained spectral density matrices where the inverses have zeros in the right places across our frequencies. And then the generative model says that our Fourier coefficients are complex normally distributed with complex covariance given by the spectral density matrix at that frequency. And this is based on that Whittle likelihood approximation. Okay, but a challenge here is the fact that we have a whole collection of these high-dimensional spectral density matrices. And if we had to do inference over all of these, we'd really, really be out of luck. That's just a huge problem. It's hard enough thinking about doing inference over one large positive semi-definite covariance matrix, let alone this whole entire set. So what we're going to do is this same thing that's typically done in the case of IID data, where we're going to take a conjugate prior. So in the IID case, the conjugate prior is the hyper-inverse Wishart distribution. And in this case, we define something called the complex hyper-inverse Wishart distribution. So that's the conjugate prior for this setting, and that allows us to analytically marginalize all these spectral density matrices and compute the marginal likelihood of our data just given the graph structure. And so we can think of this as a graph score. So you give me some graphical model, I can compute the score based on the observed data. You give me a different graphical model, I can compute the score for the data. And the cool thing about this is we can take any existing algorithm for doing search over graph structures and just plug in this new definition of what the graph score is and run the existing code to do search. So we basically transform the problem in terms of its structure back to one of standard Gaussian graphical learning. So that's what we're saying here. And so just to summarize what I said on the previous slide, in the case of IID data, we place priors over graph structures, and then based on the marginal probability of our data given the graph structure, where again to compute this relies on using a conjugate prior, then we can explore posteriors over graph structures just given our data. So here we're doing exactly the same thing, using a different definition for what the marginal probability is based on our spectral representation of the time series. So moving the time series into the frequency domain, and again, using this conjugate prior that we've defined here. Okay, so using this method, we looked at analyzing the global stock indices I presented earlier on. And if we treat those data as IID, and I should mention here we're just doing stochastic search over graphs. So if we use a standard technique for doing this stochastic search for IID data, we end up inferring a graph that looks like this, so very dense and pretty hard to interpret. But if we use our method, which assumes that there's some underlying time series, some process to this, we're not actually specifying what the model is. We're not saying it's an order 10 vector autoregressive process. We're just saying that there's some underlying Gaussian stationary process, which in and of itself is a large assumption, I'll give you that. But with that assumption, you get out much more interpretable graphs. So here we see this very strong Eurozone UK cluster. Here we have US, Hong Kong, Australia, Canada, with Japan hanging off of Australia, which makes a lot of sense. And then there's Germany, Finland, and Ireland here in this separator set, with Ireland having a connection to the US. Again, there's economic reasons why this would make sense based off a long history of connections between Ireland and the US. So at least at a first order, this is a much more interpretable structure that we get out from assuming this graph. My clicker has died, so apologies. But actually, the motivation for looking at these methods came from that type of MEG data that I described earlier. But here, we weren't looking at the word classification task. We were looking at understanding brain networks underlying an auditory attention task. So here, people were asked to either maintain their attention on some sound, and in this case, the sound was either a left tone, right tone, a high pitch or a low pitch, or they're asked to switch attention between these. And the goal was from the activation patterns over time from these stimuli to infer what is the difference between the networks underlying this activity when somebody's asked to maintain their attention versus switch their attention. Okay, so here what these circles are taking the anatomical regions in the brain. So again, for people who have looked at this kind of data, we're moving from sensor space to source space, and then we're looking at the anatomical regions and just going around and based on their proximity to one another. And these are the inferred graphs. We're going to infer a graph for each one of the setups, the different tones, high pitch, low pitch, left and right, under a focus versus switch focus task. And what we're showing here are the edges that were learned for both tasks. So these are common regardless of whether you're asked to maintain your focus or switch your focus. But what this plot shows here are the differences. So in red are the edges learned if you're asked to switch, but don't appear if you're focused, and vice versa for black edges. And if you look across these different setups, you actually see quite a few edges that are consistent. So there's some hope that there's some information here, which we're digging into a lot more right now, about whether this is indicative of networks activated in the brain when somebody's asked to switch versus focus their attention. Okay, so that was our tour into some notions of using pretty canonical tools for dealing with high-dimensional data in the context of time series. And now in the last part of the talk, I just want to quickly touch upon some computational challenges that we've been looking at. And so I want to emphasize that a lot of machine learning and statistics algorithms have the structure where there's some step where you touch every observation in your data set. Often that's called a local step. And then some step where you do an update of your parameters, often called a global step. And you iterate back and forth and back and forth and back and forth between these steps. So clearly, if you have large data, this is really computationally intensive. And it's just infeasible if you have streaming data. So instead, a really common approach out there in the literature right now is to use what are called mini-batch-based methods, where you simply subsample your data, do your local step on that subsample, and then use that as a proxy for the entire data set to do a noisy update to your global parameters. But what we're going to discuss here is the fact that this subsampling of the data is really not appropriate when you're talking about time series. So to motivate this, let's just look at one of the simplest time series models out there, which is just the hidden Markov model, which assumes that there's an underlying discrete valued latent state sequence and then conditionally independent observations. And the global parameters here are represented by theta, and these represent both your transition distributions as well as your emission parameters. And when we think about doing Bayesian computations in HMMs, our target is to infer this posterior of our latent state sequence and our global parameters given our observations. And this typically involves some local step where we update our beliefs about this latent state sequence, and some global step where we update our beliefs about our parameters. And for the local step, a really common approach for HMMs is to do a forward-backward message passing routine, where first we pass messages forward, which propagates information forwards in time, and then we pass messages backwards, propagating from the future to the past. This is the fact that per iteration, we have to run this forward-backward, which has complexity on the order of k squared t, where k is the number of states in our HMM, and t is the number of observed time points. And just to give you a sense of this challenge, we're going to look at an application with 250 million time points. So think about running this forward-backward procedure again and again and again, let alone once on this size of a data set. So really computationally infeasible. So instead, let's think about just using mini-batch-based methods. And the really vanilla approach is just subsample our observations and use those to update information about our global parameters. But of course, in this setting, if we just independently sample these observations, we're very unlikely to learn anything about our transition structure. So you might say, okay, well, I know how to handle this. I'm just going to subsample a chain of observations, this little subchain, and use this to update my global parameters. But the question is, do we just analyze these subchains completely independently, severing dependencies between them? So let's think about this naive approach a little bit more, where our local step on this mini batch would be to do a little forward-backward to get our local beliefs, and then using these local beliefs to update our global parameters. But in this case, remember, we're blocking information that we would have propagated forwards and backwards had we done the full forward-backward routine. And what we've shown is that this can actually have pretty significant impact on what we end up learning. So the question is, does this mean we just can't use these types of methods? And luckily the answer is, well, there's some hope still for using them, because there's memory decay in this process. Do we really expect that the state at time t is strongly influencing the state at time t plus a million? Probably not. So what we can do in this case is we can take our little subchain, and on the top I'm showing just a little cartoon of the true beliefs about what state we're in at that time had we done the full forward-backward, and on the bottom I'm showing what the state beliefs are if we do just a local forward-backward. But what we can do is we can, what we call, buffer this subchain and run forward-backward on a longer subchain until locally, within this thin red box, our approximated marginals are close enough to the true marginals. Because if we do that, so then based on, sorry, I was looking at the 5 minutes and I think, no, you're doing your job, It's just, yeah. Okay, but the key idea for why this works in practice is the fact that we just need a really limited buffer in most applications relative to the length of the chains that we're looking at. And so now the per iteration complexity for these local steps is just order k squared length of the buffer, and we're going to assume that the length of the buffer, length of the buffer plus the little subchain is much, much less than the length of the full observation sequence. So we looked at this idea within the context of something called stochastic variational inference. So variational inference, we take our target posterior and approximate it within a variational family, some simpler set of distributions, and then the objective is to minimize the Kolb-Leibler divergence between the distributions in this variational family and our target posterior. And in our case, our stochastic variational inference updates are going to be to subsample a little subchain and consider a forward-backward on a buffered version of that subchain, discard what's in the buffer, just look at this local chain, and then use that to update our global parameters. And what you can show, what we showed in this paper, is that using this approach, you can still prove convergence to a local mode of the objective, which is the same result as you get for standard variational inference. And the intuition is just that if you use a long enough buffer, then the noisy gradient you're computing based on off of your subsample is in the same direction as the full data gradient. Okay, so we looked at this in the context of a human chromatin segmentation task where we have 12-dimensional observations in 250 million locations. So in this task, we're thinking of these locations across the chromosome as being time points, and our goal is to segment this sequence. And so a previous approach looking at this data looked at using a dynamic Bayesian network, a more complicated model than what we're looking at. And because of the complexity of inference, and also obviously the size of this data set, they just sever the sequence into little subsections and analyze each completely independently. And their code was highly optimized and parallelized across machines, and it still took days to run. But what we showed is that using a really vanilla HMM, just HMM, Gaussian emissions, nothing fancy, but by using coherently the full data set without severing these dependencies, we're able to achieve lower false discovery rate of promoter regions, and importantly, without any truly fancy implementation, our code ran in under an hour. Okay, so that is a scalable approach to computations in time series. And to summarize in this talk, we've looked at a couple methods for scalable Bayesian dynamic modeling, thinking about low-rank embeddings or low-dimensional embeddings of the dynamics, clusters of time series, as well as graphs of time series. And then we just touched upon this idea of Bayesian computations and dynamical models using stochastic variational inference. But my group's been doing a lot of work in this area recently, thinking about scalable MCMC and handling streaming observations and things like that. In the last second, if I have it, there was so much talk about machine learning in the last talk, it triggered me to add one slide to this talk, which is to just plug this machine learning specialization. So I'm co-developing this specialization offered on Coursera, and Brazil is our second largest audience. So thank you, Brazil. But I just wanted to mention that if you're interested in learning about machine learning, this is a great way to do that. Okay, it's a 6-course sequence, so there's a lot to learn. Thanks.
Okay. So I have two questions, and they're both about identifiability. For the latent factor model, the static sort of classical factor analysis, you have to worry about the rotational invariance of the factors. Do you not have to do that because you don't care about the interpreting individual factors, or does the dynamics save you in some way? Or why do you not have to worry about it?
It's the former. So we're just interested in classification. You're talking about the first part of the talk. Actually, all of the parts of the talk that are using latent factor models. Yeah, we're not trying to interpret the latent factors at any point, and it saves us computationally not having to enforce identifiability, and the net result of what we're doing inference over is not interpreting those factors. So.
Okay, so probably the same answer is for the HMM. So if you have data that are distributed across several different machines and you are trying to get state 1 in the HMM on machine 1 to correspond to state 1 in the HMM on machine 2, then that gets to be a challenge if there's a lot of states. But if you don't care about the states, I guess you don't have to worry about that.
Which part of the talk are you referring to?
The distributed HMM thing that you talked about at the end.
Oh, this, okay. So I should say, so this is a single machine implementation that, yeah. So there's been a lot of work, typically when people have talked about SVI for time series, so I cut this because of the length of the talk, but there have been a couple papers looking at large collections of time series, and you're just grabbing them from different machines, and you're looking at each time series is going to be your mini batch, or collections of time series will form your mini batch. But here we're just thinking about a single time series and analysis of that. So there's no post-processing of state, identification afterwards.
Yeah, just a little technical. Well, actually, either one or two questions, and the answer to the first question will decide whether there are two. In your MEG, I don't do MEG analysis, and but I've seen some MEG data. And so the simple question, I think you said you analyzed with your graphical spectral model data that was averaged across subjects and averaged across trials per subject. Okay.
So again, it depends which study. So
the MEG study in the
was...
spectral analysis.
Oh, yes, yes.
So why? Aren't you averaging out all of the interesting stuff in this data?
Yeah, so no, that's a great question. So for sure, something we're interested in now is a true hierarchical model to capture variability between subjects and trials within a subject. So if we go back to the word classification task, the model in one of those papers I referenced actually has a model for variability. We do assume independence across subjects. We're just looking at performance separately for subjects, but within a subject, we have a model for variability between trials, and we're not just averaging, and we argue that that's a bad thing to do, to average. In this last study, it's really just our first pass at looking at this data. I won't argue that's the right thing to do.
Okay, so
I will say that it is something commonly done in that literature, is to average across trials to deal with the SNR, but I wouldn't argue that's the right thing to do.
Well, that triggers the second question then.
Oh, man. Okay.
Is it the case, I mean, do you believe that you can overlay this assumption of stationarity on the
No.
on the individual trial-specific level data?
Yes and no. So from talking to so clear brain data is stationary, we know that. Talking to the domain experts with this data, they've been fairly happy to assume local stationarity, and that the series we're looking at is a short enough clip that it's roughly okay. But that's a good question. Ask Nick. How short? No, it's...
Then the whole idea of using Belo approximation is questionable because it breaks down.
No,
So that
right. No, I understand. I understand. Exactly. Yeah. And so it is a very valid point that what Whittle is appealing to is an asymptotic result, the Brillinger result. And yeah, I mean, there's theory, there's practice, and this is, yeah, definitely just a first cut at this. And for this data set in particular, it's maybe not a great approximation, but yeah.